Good afternoon, everyone. My name is Michael Howard. It's my colleague David LeBlanc. And this is part one of a two-part session, derived in part from the contents of our book, Writing Secure Code, which is now in its second edition. And this is a fairly lengthy presentation. We've got about 80-odd slides to go through. And it's really derived a lot, not just, the book itself is derived from the work that we have done with the different product groups within Microsoft. The whole point of our very existence is to work with the different product groups within the company to help them build more secure software, both from a design, development, testing, and documentation perspective. And this is really a lot of the lessons that we've learned. And I'll be absolutely honest with you, I think we've seen just about every mistake that anyone has ever made. So a lot of this is first-hand experience, and hopefully by following some of these guidelines and these principles, you won't make some of the mistakes that we've seen. We're going to be sort of jumping between ourselves. We tried to break it up into some pretty even chunks, so there's no no randomness, but we will jump between us. So the agenda, and as I say, it's in two parts. First, I'm going to talk about some of the process improvements that are being made at Microsoft and the reasons why we're making them. And I think there's some interesting things that you will learn as well from the process changes that we're putting in place right now. I'll then talk about threat modeling, something we're doing as part of the overall changes to the development process. And then we'll move into the area of some of the common mistakes that we've seen and the mitigation techniques. And finally, we'll move into security testing. So the first half mainly covers the process, threat modeling, and some of the common mistakes that we've seen. And the second half, we'll move into some more mistakes that we've seen, and finally, security testing. So I want to start off with some of the security process improvements that we're putting in place right now at Microsoft. And in fact, there was a document with a whole plan for making these changes that is just about to be signed off by Bill Gates and by Steve Ballmer on improvements, basically changing the process lifecycle such that it is more cordial and more capable of supporting a development that ships secure software. The simple fact is you can't build secure software if the software is not designed to be secure and built with the appropriate techniques and technologies in place from day one. You can't sort of write crap, design crap, test crap, document crap, hunt for a whole bunch of bugs and then ship. Doing that will ship sort of marginally more secure software. You have to change the process. So I'm going to explain some of the things that we're doing. So starting from the left-hand side, this is actually one of my favorite ones, is we're actually asking more questions during new employee interviews. When I say more questions, I mean more security questions. And I don't mean how does RSA work, I don't mean how does Kerberos work, I mean what's wrong with that code on the whiteboard? Think of these threats, what are the issues? And the reason why we have to do that is we see a lot of students coming out of school who know nothing about building secure systems. They know how RSA works, they know how Kerberos works, they know how firewalls work, but they have no idea how to build secure software. To give a prime example, I interviewed two students from a very prestigious, very technical school. I'm not going to mention their name. Both of them were software engineering students. I interviewed them 2 weeks apart. Neither of them knew what a buffer overrun was. They knew they were bad, and that's about it. But they didn't know what they were. They just couldn't explain how they become vulnerabilities, which is kind of alarming when these people are both software engineering students from a technical school. So the reason for doing that is to put more, give more feedback back to the universities to get them to change some of their curricula. And we are working with some of the universities as well to help them build curricula for teaching people how to build secure systems. Team member training, I'm going to cover education very shortly, but unfortunately security is one of those areas where what you don't know will bite you. And so we think that education is absolutely critical when it comes to delivering secure systems. During the design phase, something we've added now to the design phase is threat analysis, and I'll be explaining threat analysis in a bit more detail shortly. But basically, if you don't understand your threats, you can't ship secure software. You can throw a whole bunch of security technology in there and think that you're secure, but unless it mitigates specific threats, you're really wasting your time. And so the good news about threat modeling and threat analysis is it's become almost a household term at Microsoft. Everybody's doing threat analysis. And we're working on refining the processes, and we're working on tools to help augment the process. And so you'll see more work coming from us over the coming months. But we're really gung-ho on threat modeling. I think threat modeling is absolutely important. Once the design phase is sort of coming to completion, it's expected that the development team will spend time with our group, our respective groups, going over the designs, going over the threats, going over some of the coding issues, documentation issues, and so on. And the reason why we have to do this is that our respective groups, sort of our role in life, ultimately, is to seed the different product groups within Microsoft with expertise, security expertise, so they can continue doing what they're doing, but in a more secure manner. And we can end up building little areas of security within the product groups, so they don't have to rely on our groups every day to sort of help them out. But for the moment, we're hand-holding a lot of the product groups. There are a number of product groups that are self-sufficient, and we're still involved with those product groups. But basically, we see ourselves as sort of proxy security program managers for those groups to help them deliver more secure software. The good thing is, you have to build this time into your schedule, where you spend time with our group to go over your designs. Data mutation and least privilege tests, I'm going to explain those a little bit shortly, well actually in the second half of this presentation, but we've come up with a way of working with a bunch of people in academia on a way of building more concrete and more predictable and less random security tests. And I'll share some of those findings with you. External review, we actually spend a lot of time working with external companies who are security experts, mainly because some of them have certain areas of expertise, and it's worthwhile spending some money with them to review code, review designs, and to do penetration work. It's worth the money. And it's worth it because they often look at things in a different way than we do. It's just good practice to have a separate set of knowledgeable eyes looking at the code. The bottom one there about reviewing old defects, one thing we do is when issues are found, we document, so what was the root cause? What was the problem? Because fundamentally, people make mistakes. And that's fine. People make mistakes. People screw up on a daily basis. And that's fine. Just don't keep doing the same stupid mistakes time after time. And unless you stop to take time out to say, why did this happen, you're going to keep making the same mistakes time and time again. So one thing we do when a bug comes through the Microsoft Security Response Center and ends up going out as a bulletin, there's a back end to our process that says, okay, what was the problem? Was it a development problem, a design problem, a documentation problem? What was it? How can we prevent this from happening in the future? And the other reason for doing that is this becomes like a little library for people to read. And if you read these, and it sort of puts you into a sort of evil frame of mind, and it's really good to read these before you go reviewing code looking for issues. The other thing that we do, and it started out as a skunkworks project, but it's actually turned out to be very, very useful, is once we train people, we hope that they start writing more secure code, and then the peers who review the code also understand security issues, so they find issues before the code gets checked in. But also our group randomly reviews check-ins that go into Windows. We actually look at a diff of anything that went in, say, within the last 24 hours, and we review that code, looking for security vulnerabilities, because it's a much smaller amount of code. It's much easier to look at a diff than it is to look at a whole bunch of code. The good news is to this day, since the Windows security push, we think we've reviewed about 30% of the code that's gone back into Windows. Don't get me wrong, all the code has been reviewed that's gone back in. I'm talking about our group doing an extra level of check. We have seen no security vulnerabilities going back into Windows since the security push. And that, to me, is a sign of, an empirical sign of progress. To the point where I actually saw, it was about August last year, I saw a new file get checked into Active Directory, and the file name was encryptedpassword.cpp. And I thought, you know what, this guy's obviously handling passwords, and there's all these, basically any of you who know about handling passwords in memory and cleaning memory and all this sort of stuff, you know there's a bucket load of mistakes you can make. And so it was only about 300 lines long, but I spent 4 hours reviewing the code, and did that on purpose, looking for mistakes. And I looked at this code from every single possible angle of attack, and this person had written this code absolutely flawlessly, to the point where I emailed the director of Active Directory and just said, just give the guy some money. Just, he's done a great job, just give the guy some money. In fact, I even thought he was a senior developer at some point. And it was just like Joe Sixpack in Active Directory. But he got an extra $1,000 in his paycheck. And you know what? That guy's going to continue doing the right things regardless. We do have secure coding guidelines. We actually have guidelines for design, test, and coding. Guidelines are an absolute minimum bar, absolute minimum. You should always be trying to strive to exceed those guidelines. They are the absolute minimum that anyone could ever attain. But they're basically a list of what's acceptable and what's not. We also use a lot of tools internally as well. I'll be honest with you here in the area of tools, we don't rely on tools for shipping secure software. If you got a crap developer and really great tools, you probably got pretty crappy code too. You may find some bugs and some useful stuff in the tools, but you can't rely on tools for delivering secure software. There's no replacement for human intellect. It's really important that you train the developers, make sure they're damn good developers, and understand what it takes to build secure software, and give them really great tools. And so that's what we're striving to, but we'll never hold tools as the bar to which, you can write whatever you want, and let's just hope that the tools find any bugs that you make. We do not rely on that whatsoever. Sort of bumping up to the top, you may have heard about the security push that we had for Windows. We've now had them for just about all products at Microsoft, or some of them are ongoing. The Windows security push, which Dave and I were very actively involved with, was originally slated for 4 weeks, ended up lasting about 10 weeks. At about the 3-week mark, we realized how much work we had to go, and so we ended up pushing it out to about 10 weeks. The goal of a security push, which usually happens in about the beta time frame, is to down tools for N number of weeks, more education, and the reason for that is because you can almost guarantee that the threats have changed and new concepts have been learned since the last time we did any training, regardless of how long ago the training was. More training, more penetration work, more code reviews, more threat modeling, and so on. The security audit, which we've just finished up the security audit. There's about 20 or 30 of us spent about 4 to 6 weeks on the security audit for Windows Server. The question you want to answer at the security audit phase is, are we ready to ship from a security standpoint? And that includes re-reviewing threat models, looking at any incoming bugs, and if a security bug is found, it's like, why wasn't this found? What was the problem? What was the root cause of this problem? Why did we fail? The other thing we do is penetration work, which David was especially actively involved with. The other aspect was also re-reviewing threat models, going back over the threat models, because the threats will have changed. For Windows Server 2003, we basically came to the decision that the base product was ready to go from a security standpoint. There was one little fly in the ointment. When we went back and re-reviewed the threat models, we asked the IE guys to go and consider the threats to a domain controller when an admin is browsing from that machine. Just look at that one scenario. What are the threats? Not the vulnerabilities, not the bugs. What are the potential threats? Because you have certain enabling technologies like ActiveX, JavaScript, VBScript, Java, and so on. And basically it's like, this is unacceptable. These threats are unacceptable for a domain controller and for a server. And so the net result, for those of you who are not aware, you've got to realize this is actually what happened. In fact, we're just sort of wrapping it up now, is we have turned IE on server by default into an HTML 3.2 browser. It does no JavaScript, it does no VBScript, it does no ActiveX controls, it does no Java, and it hosts no .NET Framework applications either. And the reason is, it's a frickin' server. The last thing you want is some idiot browsing from a domain controller and getting whacked and taking out the domain controller. The domain controllers are sensitive, very important machines. You don't want the machine getting whacked. And so by default, the attack profile for IE has been dramatically reduced. And you know what? If you want to turn the things back on, that's fine. But that is not the default out of the box. And I take my hat off to the guys who pushed that through, because when we first turned it on, we found a whole bunch of regressions. There's a whole bunch of other stuff that failed to work. And the decision was that any issue that cropped up got fixed. We're not backing down from changing the default settings of Internet Explorer. You got to realize we're just wrapping this up now. It would have been very, very easy to say, you know what, this is just too hard. Let's go back and turn back the normal default settings of IE, and so these regression problems don't happen. But instead, the team decided we'll fix any regressions, and we'll stick with the default secure settings of IE. So the whole point of a security audit at this point is, are we there yet? And last, but by no means least, is the whole notion of learning and refining. We can only design, develop, test, and document applications based on the threats we understand today. And the threats and the attack vectors and the attack techniques change over time. And so we know there will be bugs and security issues in Windows Server 2003. We know that because we can't predict the future. But we've done a great deal of work to reduce the attack profile of the box to reduce the potential for damage. Something else we've also been working on very strongly is this thing called SDQ plus C, which is a way of thinking about when you're building apps. You got to make sure you have some aspects of the design and development process that cross each of these 4 areas. So when you're building something, you have to think about secure by design. In other words, is it a good, sound, secure architecture? Reducing vulnerabilities in code. That includes reducing vulnerabilities in code that's currently shipping. In other words, go looking and removing them. But the ultimate goal is to not put the vulnerabilities back in there in the first place. If you go hunting for bugs, it means you're looking for things that are already there. We should be changing the process, which is the whole point of this, such that the security vulnerabilities are not added to the code in the first place. The area where I spend probably 75% of my time is in the next area, which is secure by design. I am a huge believer in just turning stuff off unless everybody needs it. And we sort of set this bar, it's sort of a bit of a fuzzy bar, which is if 80% of the population doesn't require that feature, you turn it off. And you allow it to be turned back on easily, but it's not there by default. And this is something we've done dramatically in Windows Server. Windows Server 2003, when it boots, basically does nothing. It basically is nothing. I mean, it comes up and says, okay, I do nothing. What do you want to do? And you can opt for what you want sort of the role of that machine to be. I want it to be a DNS server. I want it to be an IIS server. IIS is off by default. And when you turn IIS on, it does nothing but serve up static files. If you want to do something else like ASP, ASP.NET, Internet Printing Protocol, Index Server, CGIs, whatever, you click on those options. But by default, they're all off. And the reason is that admins don't necessarily change their boxes very often. Don't get me wrong, there's like a bell curve of users. There's those who are ultra paranoid, who change absolutely everything. We don't need to worry about those guys. They can take care of themselves. At the other end of the bell curve is the people who just don't care. And no matter how much work we do, then they're never going to care anyway. And then in the middle, there is the vast quantity of people who want to do the right thing, but they don't know what the right thing is. And so that's why we need to ship a more secure default that basically does nothing. And then you elect for the functionality because we know that people don't turn stuff off. In the area of secure deployment, one of the big ones here is patch deployment, which has always been, people don't like applying patches. There always will be patches. It doesn't matter what the product is, doesn't matter what the operating system is. Ultimately, what we want to do in the short term is make deploying patches easier, and then in the long term, have less reliance on patches. And so we're working on having a common patching technology, which is now being put in place, and just making it easier to deploy patches. And the last one is when you're designing things and building things, you have to think of, okay, who are my customers? What do I need to make those people aware of? What do they need to know about the security implications of this feature? What happens here? What happens there? And so on. And I take my hat off to the SQL Server guys, because in Service Pack 3, they spent a lot of time documenting the security implications of certain functionality, so people are aware of what the issues are. So the critical thing that we've learned over the last year is education. You've got to educate people. You can't expect a whole bunch of people who know nothing about building secure systems, and we assume people don't. You have to assume that. You can't expect them to understand how to build secure software if they know nothing about it. How a bunch of people who know nothing can pretend they know about something still amazes me. You have to make sure these people understand what the issues are. We also, as I mentioned before, we kind of teach some of the wrong things in school. I'm not saying we teach the wrong things. We teach them how security features work. And that is important, but it doesn't help you build secure software. Understanding how RSA works does not help you build a secure system. It's a little bit like going to school and saying, okay, today we're going to learn about defensive driving, and what you're actually taught are the innards of an internal combustion engine. That doesn't teach you to be a defensive driver. Sure, you know how the engine works, but it doesn't help you. You still go around a wet corner and apply the brakes and wonder why the car spins round. So we need to move more into the area of teaching people about what it takes to build secure systems. And you can read the rest. Oh, the other one is security features does not equal secure features. Just because you have a whole bunch of security features doesn't mean you're secure. Not whatsoever. Because they may not mitigate the appropriate threats, which I'll cover in a moment. And so just on the notion there about education, we now have mandatory security training in place for new employees who are working on product groups. If you're a developer, a tester, a program manager, or a network operations person, you must go to training within 3 months of joining that product group. And in fact, on Wednesday morning, I spent 4 hours training the latest crop of Windows developers on all the latest issues and what they should be aware of and where to go for more information and just raising awareness and making them understand what the issues are, because we assume they don't know. So let's move very quickly to some of the design requirements. Now we're very strong on the design aspect now. We teach a lot of people about the fundamentals of what it takes to build secure systems. One of the biggest ones is reducing your attack surface. A lot of applications ship with a lot of features enabled by default. And unfortunately, if the feature is there by default, it's the old adage, if you build it, they will come. And unfortunately, in this case, they are attackers. If you can build it, the attackers will come. And so it's important that the feature is not on by default, because if it's not used by everybody, it shouldn't be on by default, because if it is on by default and there is a vulnerability found, the urgency that is required to deploy that patch by administrators is very, very high. Now, if the feature is off by default, the urgency with which those patches need to be deployed is a little bit more slower paced. And people like that. So the critical ones here are defense in depth, multiple layers of defense. The number of clients I've spoken to where they said, well, we're secure, we're using a firewall. Firewalls are not walls, they're misnamed, they're fire speed bumps. They slow people down a little bit. They don't necessarily stop people. And anyway, what's the only port that's open? Port 80. So always ram everything through port 80 anyway. HTTP, it should be renamed, like port 80 should be the Universal Firewall Traversal Protocol. That's exactly what it is. And so because you have a firewall in place, it's kind of irrelevant, because you can just drive a hole straight through port 80. So the next person who says, well, we're secure, we're using a firewall, I'm just going to scream. But there's some software that's like that. So it's like, well, what happens if the firewall's not there? Well, we're screwed. Well, that's not a good enough answer. There is some stuff that requires extra levels of defense. An analogy that I have, which is a really stupid analogy, is the thing in our house, my wife and I's house, which is probably the most expensive and most tantalizing to a thief, is my wife's jewelry. It's expensive, she's got lots of it, it's easy to transport, and it's easy to sell. And so the defensive mechanisms that are in place to protect that jewelry are extensive. I mean, to get to my wife, here's a recipe to get to my wife's jewelry. The weakest point into the house is through the garage. I'm assuming you're through the garage. It's not a big problem. There's actually a dead-bolted door between the house and the garage, rated at 30 minutes with a gas axe and tools. I'm assuming you're past that. Then you've got to get past the alarm system. There's actually 3 parts to the alarm system. I'm not going to go into all the details, but there's motion detectors, there's infrared detection, and there's perimeter defense as well. The guy I bought the house from was a retiring Boeing exec who looked after their missile defense systems. So he was pretty gung-ho on security. My wife bought the house because of the views of Mount Rainier and the Cascades. I bought it for the alarm system. But I'm assuming he got past the alarm system. Now I got 2 guard dogs, 2 Yorkshire Terriers. Now, Yorkies, they won't take you out. They won't take you out, but I'll know if you're in the house. So I'm assuming you get past the guard dogs. Just throw them some meat. They're taken care of. Then you've got to find the safe. Now, you may be thinking, well, hold on a minute. He's hiding the safe. This is security through obscurity. We've always been told that security through obscurity was bad. No. Security through obscurity sucks if it's your only defensive mechanism. If it's part of a layered defense, it's completely valid. Then I'm assuming you found the safe. Now you've got to get into the safe, which is rated at 60 minutes with a gas axe and tools. Even then, we have insurance. So there's some stuff, like if you're on my skis, get through the garage door, you got the skis. You know what? I need new skis anyway. But to get to the really expensive stuff, you've got to get past multiple layers of defense. And there are some aspects to security and software where there's some stuff that's so sensitive, you have to have multiple layers of defense. And a firewall shouldn't be the only defense necessarily. Then there's a notion of least privilege. If you run, I'm not logged onto my laptop right now and haven't been for 3 years as a member of the local admin group because people want to whack me. I know they want to whack me. And if I run some malicious code and I'm an admin, then the code runs as admin, and what can admin do on the box? Anything it wants. They may be thinking, well, Michael, you're a little bit paranoid. No, people are out to get me. I absolutely know they are. In fact, the director of our group is out to get me. And the reason why is if you see an email that's sent to you and your peers and your boss that says, fire my lame ass, it came from you, kinda. The problem was I walked past your office and you left the workstation unlocked. And so you sent an email to your boss and to your peers and back to yourself to say, fire my lame ass. So now everyone in our group wants to get me because I've gotten a few people, including our director. I've got him twice. So he's really out to get me. Well, one day, the thing is, George is actually a pretty savvy guy, and one day I received this email, and it said, how much did you pay for your D100? Now, this is a wonderful social engineering attack, because I just bought a Nikon D100, which is the digital SLR, 6.5 megapixel SLR camera, and it's not cheap. And at the bottom of the email, it had a link to eBay. So of course I clicked on it. It's a wonderful social engineering trick. Obviously someone is selling D100s for a lot less than I paid for it. And so I clicked on the link, and IE popped up and AV'd. That's strange. Shut the browser down, clicked on the link again, IE came up, AV'd again. Well, that's strange. I did it again, it came up AV'd, I threw it into the debugger, and it turns out George was doing some really funky stuff and was trying to write something to the System32 directory in a bug that was fixed in IE that day. And he tried to do some funky stuff onto the System32 directory, but you know what? I'm not an admin. And so the whole thing failed, and the net result was just IE, the exploit code just AV'd. And so I'm not an admin, and I took great delight in telling George that his code sucked. Anyway, least privilege, we spent a lot of time with a lot of people telling them what the main issues were with least privilege and why you need to get out of it and how to get out of it. Security files, I've already mentioned that. I'm not going to go into any greater detail. Learning from past mistakes, that's in that timeline that I showed you. There's time at the end when issues are found, feeding that back into the process. Security as a feature sounds sort of motherhood and apple pie. What I'm getting at here is if you don't building time in the timeline for education, for security pushes, for security reviews, and so on and so forth, you're going to wonder why your schedule has slipped. And so you need to build in that time into the schedule. And the last one is we're asking now people to think more about application diversity, making applications look slightly different from installation to installation, and whatever that means for that installation itself. So that way, there's a more heterogeneous environment so that things like worms may not spread as fast, and security issues may not affect as many machines. With the caveat that you also have to make sure the system is supportable as well. So I'm going to go through very quickly through threat modeling. If I had my hands tied behind my back and I could only do one of three things, threat modeling, code reviews, and better test plans, I would do threat modeling every day of the week. And the reason is they uncover so many issues. The ultimate point here is that you really can't build secure software unless you understand your threats. You could say, yeah, well, using SSL, using IPsec, we've got some ACLs in there, we've got a bit of Kerberos and some DES and a firewall and some RSA, and you may win the game of buzzword bingo, but you still ship crap because you didn't mitigate this threat, which is a real glaring threat. But you slept well at night because you had SSL enabled. I mean, a lot of people don't realize, but well, they do realize. I don't think they want to admit it. But when the data leaves that channel, an SSL channel, and it's persisted at either end, it's not protected by SSL anymore. And so you have a whole bunch of threats to that persistent data. If you don't understand what those threats are, you haven't mitigated them using SSL. I can tell you a story about that, but I can tell you in the break if we have time. I'm not going to go through all the details, but I got a great story about a bank that used SSL and thought they were secure until it was proved otherwise. The other thing is they find threat models, if they're used as a sort of debugging tool, which is generally when it's late in the process, find different issues than code review and test plans. If they're used as a technique, which is what's happening now, earlier in the process, they prevent you from adding vulnerabilities and design flaws to the system ahead of time. If you think about it, code reviews and test plans find issues that you've already added to the code. Threat models, if they're done early enough in the process, which is what they should be done during the design phase, prevent you from putting issues in the code in the first place. And so you save a lot of time doing them. But they do find different issues, primarily because code reviews and test plans tend to find implementation flaws, and threat models tend to find much higher level design issues. If these conditions exist, then we may get attacked this way. Also, the other thing is we found that about 50% of your bugs will come from the threat model, depending on the product. But we found about 50% will come from the threat models because they're different issues altogether. The threat modeling process, I would say that a year ago, threat modeling, and in fact the version of threat modeling that we originally documented in writing secure code, or I'll take the fall for this one, that I documented in writing secure code, was don't worry, I'll point out your problems, was random. I mean, it really was random. It wasn't scientific, it wasn't predictable, it required too much intelligence and too much security expertise to pull off. Over the last year or so, because we've mandated threat modeling, and it's amazing what happens when you get a whole bunch of people who are not security experts doing threat modeling. It's amazing what issues they find. It's amazing how you can sort of learn to make the process better when normal human beings are doing the threat modeling. And so now we think we have a pretty good handle on how to do threat modeling and make it more reliable and less chaotic. So the process is fairly straightforward. First of all, you need to get a model of the application. We tend to use data flow diagrams. You can use whatever is appropriate. It really doesn't matter. Ultimately, what you want to end up with is a list of components in the application that are going to get whacked. Because all these things are going to be targets of attack. And you need that list. And you need to know the communications that go on between the different processes to understand what the threats are. Then what you do is, from the different nodes or the different components that come out of the data flow diagram, is you ask, okay, so this component could be a process. What kinds of threats is it susceptible to? So here's an example. You've got a data flow that goes between a client and a server. Very simple example. Can I spoof that data? Can I tamper with it? Can I repudiate that transaction? Can I view it? Can I deny service to the process? Can I elevate my privilege? And then what you do is you come up with trees of attack, or threat trees, to say what conditions must exist for this to become an actual reality. And in the first edition of the book, we actually thought that STRIDE was threat modeling, and we were dead wrong. STRIDE, I was wrong. STRIDE is basically a way of thinking about categories of threat. I'll explain why that's an important thing very shortly. Finally, you rank threats. We have this thing called DREAD just because it's appropriately alarmist, and it's just a way of ranking potential risk. Some people just sort of pony up risk based on how hard is it to pull off and what sort of damage could occur if this attack actually is manifested. And so we just use DREAD as a fine-grained version of that. Like, what's the potential for potential damage? How reproducible is this? Does it happen once? Does every attack succeed, or is it only one in 100,000? How exploitable is it? What sort of expertise is required to pull this off? Is it a script kiddie attack, or does it require some deep knowledge? Affected users, does this affect everyone or just a couple of people? And finally, discoverability, we just say everyone will always discover these things. And so it's just sort of added as a high priority always. So let me give you a quick example of what one of these threat models looks like, or at least a portion of the data flow diagram, and then building up the threat tree to come at the attack. So this is just one node in a data flow diagram. It's a process, which is pars request, whatever that means. You think, okay, are there spoofing threats to this? Are there tampering threats? Are there repudiation threats? And so on and so forth. And then we can come up with is actually a list of conditions or subthreats that must exist for this threat to actually manifest itself. And you'll notice at the bottom there's two conditions which are ANDed together, so both those conditions must exist for the subthreat to exist. So when you're looking at these nodes in the threat tree, you think, is this item susceptible to spoofing? Can I tamper with it? Et cetera, et cetera. The good news is, if using data flow diagrams, it turns out that certain threat types apply to certain aspects of the data flow diagram and not others. And the reason why that's a good thing is it reduces the amount of work you have to do when you're building the threat model up. I'm not going to go through this in detail. The slides themselves actually have notes at the bottom that explains it in greater detail. The other thing that's interesting is we found that from threat modeling is that certain types of threats can lead to other kinds of threats. So as an example, if you have a threat which is, if I can replay someone's credentials, then I can spoof them. That's the essence in STRIDE there. If those credentials are an admin's credentials, I can replay them, elevation of privilege. It turns out that one of the core threats that lead to that is being able to access the credentials across the wire. That's an information disclosure threat. And for that to be a worry, you must be using, for example, basic authentication and no SSL. And both those conditions must exist. And finally, with threat modeling, finally in terms of the tree stuff, you can actually use apply tree pruning techniques whereby an ultimate threat can exist, but you can say, well, you know what, if one of these conditions is mitigated and there's an AND clause there, then this whole side of the threat tree just becomes mitigated because you've mitigated one condition. And then by using dread, you can say, well, that has a bigger dread rating, and so the one on the right-hand side is where we should start focusing most of our effort. That doesn't mean you don't look at the other one, you absolutely do, but when it comes to priorities, the one on the far right is the one you go looking at first. You apply most of your review work, most of your test work, analysis work, and so on, because that's where the most damage is. The cool thing about STRIDE when you're looking at threat modeling is that the different threat categories actually have mitigation categories. So for example, spoofing can be mitigated with good authentication, as an example. Tampering can be mitigated with good authorization, like access control lists or permissions. For ephemeral data, as it flies across the wire, say a message authentication code, et cetera, you can read this as well as I can. But the core message here is if you have a bunch of threats, and this is a spoofing threat, this is a tampering threat, there are broad categories of mitigation techniques you can apply. And notice I say techniques, not technologies. The technologies are determined by the techniques and the infrastructure around you as well, because there are other things that go into making the technology decision. Coding to a threat model, the critical thing here is that when you get the overall risk of an attack or the potential damage from an attack, this helps determine where the developers will spend most of their time making sure that the code is not vulnerable to attack. Now the last one, which we never expected until a bunch of testers in Windows started thinking about this. I hate to say this, but a lot of testers, and I've spoken to a ton of testers inside and outside of Microsoft, but a lot of testers feel like they're the poor schmucks cleaning up after the developers. When you involve testers in the threat modeling process, they feel the love to start off with, but the other cool thing is that the testers now have threat categories which have mitigation techniques. And mitigation techniques have attack techniques. So now, not only do they have a list of things they need to test, because for every single node or every single threat in the threat model, there should be at least 2 test plans. One to prove it does work, and one to prove it doesn't work, if you know what I mean. And now they have a list of the things they have to go and test. And they have mitigation techniques, so now they have attack techniques for those mitigation techniques. Examples. So if you decide you've got a spoofing threat, you may decide we're going to use strong authentication. Well, a tester can start doing things like, I'm going to try and brute force the credentials. I'm going to try, can I replay the credentials? Can I downgrade to a less secure authentication scheme? Like, I don't support Kerberos, I only support NTLM. And then you can download to the lower authentication scheme. I've seen websites where they've had, say, digest authentication, which is marginally more secure than basic, but they support both, and normally the browser would probably choose digest. However, I've seen people write code where they say, well, I don't support digest, I only support basic, and they got a much less secure protocol. And what's even worse is that the credentials that go across the wire are very easily intercepted, or they can be replayed unless they're protected by an SSL channel. So now the testers have got a way of thinking about how to attack the system. And rather than just being random, they now have very concrete ways of attacking the system. I'm not going to go into all these in any great detail. They're in the slides. So some sort of critical action items. I want to repeat again, if you're not doing threat models right now, you've got a bucket load of issues you don't know about. And most importantly, if you're designing new stuff or building new stuff, you really need to have a threat model in place. Otherwise, you're just shooting in the dark. You do not know if you've mitigated the appropriate threats. You do not know. You may feel warm and fuzzy because you won the game of buzzword bingo, but you may not actually be secure from attack. So threat models are, to me anyway, from the results that I've seen inside Microsoft, are worth their weight in gold. And basically, you're not done on the design phase until you have a threat model in place. And with that, over to Dave.
Okay, they moved us from the room that had the monitor switcher, so I'm going to use the low-tech monitor switcher here. Let's see if I can get it to go. Okay, let's. Sorry about this. Okay, let's see here. All right. Okay, we're going to talk about some common coding mistakes. I'm also going to have some examples for you. Hopefully it'll make things a little more real, a little more interesting. I'm going to talk about some of my favorite types of errors. First of all, I'd like to talk about least privilege errors. So these are a pretty common thing. I mean, how many of you have tried to say, do like what Michael does and run as, you know, user or power user? Anybody? A couple here and there? And how many of you find that some stuff just doesn't run? Like games, whatnot, that sort of thing. Well, why do I need to be an admin to run a game? Doesn't make any sense to me. I don't get it. Yeah, those people are not practicing least privilege. And so if my game happens to be, say, network aware, as more and more popular games are, then we could very easily run into a situation where, you know, if there's a vulnerability, anybody running the game is going to get nailed really pretty badly. So one of the first things we want to do is we want to use only the access required to actually perform the task at hand. If you need to read a file, you want to open it for read only. You don't want to just open it for everything. And this seems really obvious, but it's a very, very common mistake. When you go through and start diagnosing why some of these things don't work, you're like, oh, well, it fails reading this registry key. Well, why did it fail? Well, because it tried to open it, you know, all access. Well, did it really need all access? No, it was just trying to read the stupid thing. Okay, so this is a very, very common error. And it's one of the fundamental principles at which I try and look at running code. Does this service really need to be local system, or could it be something less? So that's a really important principle. And, you know, it's pretty obvious. I mean, if you're running as administrator, you're running as a high-level user, local system, something like that, and something does go wrong, you've got a catastrophe on your hands. Okay, it's usually an access control list issue, and it frequently comes from writing configuration data and other types of information into public areas instead of per user areas. So a lot of times if people just modify writing to HKey current user instead of HKey local machine, a lot of these problems just immediately go away. Yet another item that I think is quite important is to let the user know what goes wrong and to fail gracefully. I don't know how many times I've seen situations where people fail to check. They just assume that something's going to open. And so then the failure mode really becomes quite spectacular. All sorts of interesting things go wrong. And the problem with that is that it takes a long time for support to figure out why the customer is failing. And then it takes a long time for the tester to figure out just what in the heck is going wrong here. And then it may take a good long while for the developer to fix it as well. So if you fail gracefully and print out some sort of recognizable message, cannot open such and such, well, it'll lead you directly to the piece of code that's actually causing the problem instead of wandering off 3 functions later and then having some sort of failure because something that you assumed was going to happen actually did not happen. Lastly, let's always make sure that we test as non-administrators. I mean, developers almost always run as administrator on their system unless they're Michael, okay? And so all sorts of things work only if you're an administrator, and then they find them out later. I actually had an interesting experience with a pretty sensitive internal application that my group was called in to do some design work on. And so we set up a mock-up of it in our lab, so it was like a copy of the whole thing in our lab, and it was running away. And so the first thing we wanted to do was see how much we could tighten down security configurations on all these boxes. And so we went through and we tightened every screw that we could find, and we expected it just to blow up and have to do a lot of work after. Worked marvelously. Everything just kept on right on working. We said, "Whoa, great developers, this is great." Then the next thing we did was we changed all the administrator passwords on all the different boxes. And it instantly blew up and quit working and took 2 days to fix. So what happened? Well, when they were developing the app, they'd used administrator accounts and they'd set the same password on all the different administrator accounts. And so when you changed that, it all just went totally sideways. So if they'd actually been testing as non-administrators, which is what the thing was supposed to be running as anyway, then they would have found these things and it wouldn't have cost us some couple of days of downtime. Okay. Now this is one of my personal pet peeves. Client-side security isn't. It does you little to no good. There's some cases where you want to check your business logic in, say, 2 different places because you don't want to make an expensive round trip to the server and back just to find out that the zip code's required, for an example, okay? But if it's important from a security standpoint, we've always got to make sure that we're enforcing all of our checks at the server. So we never want to assume a well-behaved client, and likewise, when we're writing the client, we never want to assume a well-behaved server. Somebody might be able to trick us into going to the wrong server. So that's something else to think about as well. So it can go both directions here. It's also very, very important to not build in access control checks into the actual client application itself, but to instead rely on the access controls that are on the underlying operating system. One example is in earlier versions of the operating system, you had to be an administrator to reconfigure the network parameters. Okay, well, why is this? Well, it doesn't particularly make any sense. I could go change the access controls on the registry keys that control the network, and then somebody could come along and directly modify the registry and change the networking parameters, and it would all actually work. Well, that's not really a fun user interface to have, and it's not a good reason to have people running as administrator just because they've got a laptop and they need to move from one network to another. Okay? So what we did was we took out this check for administrator that was actually embedded into the client, and instead just checked to see, can we read and write these registry keys that underlie these things? And then we created a network operators group and DACLed the keys correctly and now you can put users into or out of that group, and now people can actually get to things. So that's a smart way to do things. I mean, instead of, because as soon as you go and embed something in the client, and then it turns out that the access controls are just a little bit different, now somebody gets real smart and figures out they can go around it, and now they've got an exploit. Now, whether it's really an exploit or not may be arguable at that time, but they think they do, and it's going to be quite a bit of trouble from there. Okay. Next is running services. Running services is something that's of really great interest to me because part of my job at Microsoft has been operational security. And so I want to go find out if our operational deployments are actually secure. So I get to go try and break into things. And if I do break into things, then I have to go figure out how to fix it. And services have been a difficult area because if I can compromise a machine at administrator level that's running a service, that's running as somebody that I want, then I may be able to subvert that process to go do something completely different. For example, SQL Server running as a highly privileged domain user, I can pop an XP command shell, and now I can do all sorts of interesting things, for example. There's a lot of other ways around this. Okay, so the best way to do this is to mitigate the threat by thinking about how you're going to run as a service. What sort of users are you going to run as? The worst possible thing that you can do is A, require that your service be highly privileged on all boxes that it runs on, and B, require that it has a domain level account. That's when you'll create the maximum trouble for your administrators and the least trouble for anybody that might happen to come along and try and attack these people's network. So what we'd like to do instead is use two new things. One is local service and network service. The difference between these is basically a stripped down version of the local system account. You don't have to worry about changing its password all the time. It'll reset itself. It has very, very few rights on the local system. And the only difference between the two is the network service actually has credentials off the system under the guise of the machine account. And local service really can't get off the machine. Okay. Now, this ought to be really pretty straightforward. You've probably seen several demos of buffer overruns and how to create them and all sorts of things going on in that area elsewhere. Your pretty basic run-of-the-mill standard buffer overrun is pretty straightforward. You've got a variable declared on the stack. You overrun it, and away we go. If you get lucky, it might just crash your app. If you get unlucky, then people are running arbitrary code using your app. And if you get really unlucky, they'll take over large numbers of machines on the internet with your mistake, which is not a lot of fun if you're the developer. Okay, so what does the stack look like just normally on a stack-based buffer overflow exploit? We've got our buffer, we've got our return address to where we came from, and then we've got the arguments. Okay, so what we can do if the buffer is dangerous is we can overwrite that return address to point back to the beginning of our buffer. We can also point it sometimes at the beginning of a buffer elsewhere. Maybe somewhere they allow me to give them 64K of data, but at this place there's the overflow. They only allow me to give me, say, 12 bytes or so. So I can leverage this to go different directions. So just because this particular buffer overrun is only, say, 12 bytes, you say, well, nobody can make a shellcode in 12 bytes. that's not good enough unless there's no other inputs to that system. Personally, I try not to ever worry about, is it exploitable? I always assume that it is exploitable. Just fix the bad code. You know, a good way to just get me to go totally ballistic is to say, well, you know, I'm not going to fix it unless it's exploitable. And then I like get out the baseball bat and go after them. So we add these together. Now we've got the return address copied over, and then away we go. So that's a pretty standard run-of-the-mill buffer overrun. Now here's kind of the basics behind a pretty real-world common mess-up. In the Windows operating systems, or actually the Windows NT line of operating systems going up into Windows 2000, XP, et cetera, the native character format is Unicode because it was built to be internationalized from the start. Okay? So things are a little bit different in there. So what we want to do is check for the number of characters, not the size of the buffer. Anybody see the mistake here? No? Okay, then I'll explain a little more carefully. Hey, we've got a...
I know it.
You know it? Oh, okay. We've got a 256 character buffer. That buffer is 512 bytes long, okay? Now, size of buff is 512. Strlen of input could be whatever input is. Now, in the case where strlen input is between 256 and 512, now we've got an exploitable condition. We're going to overflow that buffer. And so then we use swprintf, which is completely unsafe under anything except for very, very trivial circumstances, and then away we go. So the correct way to check for the character count or the count of any type of array of structures or anything like that is size of the overall buffer divided by size of the element. Okay. Now here is something, you ever heard of the dot printer overflow? If I'm not mistaken, I think NIMDA may have used it. Is that right?
I remember.
Okay. The dot printer overflow was one of the more widely attacked problems on the internet. There's a lot of exploit code out there for this particular overflow. And what you're looking at here is the code that caused it. And because it's a little bit complicated, think back to the code that I just showed you on the previous slide and think about how what's going on here. We've got a computer name that's actually in Unicode. T-chars go back and forth depending on Unicode's, whether Unicode's defined or not. And so in this particular case, it's Unicode. And T-chars, in my opinion, are actually a little bit dangerous. I personally like to work with things that are explicitly defined one way or another because I don't like to go rooting through trying to see 12 levels up if Unicode's defined or not. And then we're going to, let's see here. We're going to check and see what the size of the buffer is instead of size of buffer divided by size of T-char, which is what should have been done. And then we're going to proceed to try and stuff up to 512 bytes into a 257 character long buffer. And so it's twice the size of what we're going to tell it. It's twice the size that it actually is. And bam, away we go. So that's kind of a more boring, very routine, standard sort of buffer overflow. Now let's get on to something that's a little bit more interesting. Okay, some people think that just because something is declared on the heap, it's allocated, that it's not exploitable. This is not true at all. There's a very interesting presentation by Halvar Flake, who's here this week, on exactly how to exploit heap-based buffer overruns. It's kind of technical and it's a little bit long. We've got a lot of slides, so I'm not going to go into great enormous detail about that here. It's also been covered in several other presentations here and there, so I'm not going to get into it. But basically, the bottom line to remember is that a heap overrun can place 4 bytes in any arbitrary location. Okay, think about that. That's very, very dangerous. I can overwrite variables. I can change program execution. I can cause things to hop from one buffer to another. So it's actually a little bit more versatile in terms of what you can do with it than a simple stack-based overrun is. So it's a pretty dangerous thing. Freeing the same memory twice can also get you in trouble. Now, index overruns, these are a lot of fun. This is something that basically this occurs when, say, I go to my POP server, for example, and say, how many messages did I have? All right, well, I've got 10 messages. Okay, so then I go and allocate enough room for 10 messages, and then say, all right, give me the first message. It says, all right, here's message 12. Bam. Now I'm writing off into who knows where. Now, in some cases, what this can do is it can cause me to loop around back to the bottom of memory. So, I mean, just consider an array of, say, 4-byte integers. If I tell you to write integer 4 billion in something, it's going to cause you to loop back around and write stuff that's actually below in memory where you started at. So again, it allows me to tamper with memory anywhere in the process space. And so that's a very, very potent attack. You can do a lot of stuff with that. Okay. Now, integer overflows are also a lot of fun, and it's something that is of increasing importance to the attackers. They, people are starting to get smart about static buffer overruns, heap buffer overruns, this type of thing. And so people are actually starting to figure out exploits for integer overflows. And so basically what this is unlike a floating point overflow, an integer overflow, it doesn't matter, okay? Say, for example, the range for a character is 0 to 256. If I add, or 255 rather. Okay, so if I add 1 to 255, what do I get? Not 256, I get 0. If I subtract 1 from 0, I don't get -1 really, I get 255 back again. So these things roll over, all right? Now, you can also get truncation happening where, for example, I'll cast something downward from, say, a 4-byte integer to a 2-byte integer or therefore. And this is also fraught with peril. So look for these types of casts and that type of thing, and think about what you're doing with these. There's a surprisingly large number because most developers are not well aware of these, and they're frequently exploitable. Let me pop to an example. Okay, so let's see here. What we've got is we've got a quick little function called allocate elements. And there's a number of really pretty common applications that are used on the internet that have routines very, very similar to this, and many of them are exploitable. Anybody see what the problem is in allocate elements? A couple of you. Okay, good. What we're going to do is we're going to take two unsigned shorts. Those are 2-byte integers, one for size and one for count. We're going to multiply them together, and then just to make an easier demo, I'll print out how many bytes we're allocating, and then we'll try and allocate that number of bytes and return it. Okay? Now, as we go down, so then what we'll do is once we've got that number of structures allocated, then we'll go and write something into each and every one of those until we get to the end of everything. Then we'll free a buffer, and then we'll complete. Okay? All right. So let's use just pretty normal numbers. Okay, we allocated 32 bytes, everything worked, it's all fine, life is good. And now let's try something maybe a little more interesting. Okay, got 16,000 times 4. All right, that's 64,000. We've still got enough room, just barely. And now we've allocated 14,000 bytes to hold what we're trying to put 80,000 bytes into, and we get this. We've encountered a problem and needed to close. So down we go. Bam. Now, this exact type of problem has been turned into actual live exploits in people's code that's out there right now. Where it also comes into play is, let's say that you have some sort of document format that's going to embed information inside itself, how many elements there are, what the size of these elements are, etc. And then you're just going to go merrily along believing whatever the document told you because, well, of course, you create your own documents, and nobody's ever going to create a malicious document now, are they? And then somebody goes and creates a malicious document, sends it to one of your users, and bam, now they've got a lot of trouble. So that's another area where exactly this type of problem can bite you. Okay, here's another one of my favorite pet peeves, is partially because back when I worked for my previous employer, I had the thankless task of porting, about 50,000 lines of pretty bad code to Windows NT. And it had zillions and zillions and zillions of signed, unsigned mismatches, truncations, etc. And fairly often, these signed, unsigned mismatches caused all sorts of interesting problems, like while receive, write to file. Well, what happens when a receive returns -1? Now I'm going to try and write 4 gigabytes to file. That's going to work real well. Okay. And you can also run into problems where you've got you're going to cast things to a signed integer when it really shouldn't be cast to a signed integer. So we're going to take the length of the string here and pop it into len, and we've got buff len here. So if if len is large enough, it's going to become negative. So if strlen is really big, then we're going to get a negative number for len. And now len is less than buff len, and bam, away we go. There's a lot of variations on this. So the first thing is your compiler is trying to help you. Every time it complains about something, it's trying to say, hey, there's something wrong here. Pay attention. Okay, so don't just blindly cast away compiler warnings. Think, maybe that stupid compiler is smarter than I am. If you haven't had enough coffee that day, then it might be true. And also, don't think about whether or not you're using signed or unsigned integers, because basically they default to signed, and most of the time we don't really need signed integers, we need unsigned integers, because most of the time we're not really dealing with negative numbers. So if you're never dealing with a negative number, use unsigned. It's pretty simple.
I use size t.
Use size t?
Size underscore t.
Size underscore t is absolutely great. It helps you just get out of all these types of things. And another thing that actually helps is to use C++ extensions. Even if all you're writing is C code, use CPP, because it enforces stricter type checking, and the compiler will warn you about more mistakes. And that's always a good thing. I mean, personally, I prefer to write in C++, but even if I'm not writing in C++, it's a good thing to put a CPP on there. And there's also compiler switches you can use that will actually force it to check it as if it were a C++ file. So that's helpful as well. Okay. Now, format string bugs are really quite a bit of fun. I believe David Litchfield gave a good demo of that in the session previous to this. And they're really a very, very interesting problem. It's one of the few new things that's come along in the last few years. And it's actually pretty simple. Printf is supposed to take a format string and then some number of arguments. Well, some people just get lazy and decide that whatever the message is, we're just going to stuff in there and make that the only argument. Well, that's a prescription for disaster. And I'll show you how this works. Okay, so we've got a pretty basic little main function here. We're going to try and open a file for read access supplied by the user. And if we can't open the file, we're going to print a message, and based on whether or not it's a really horrible error or it's a bad error, we'll print some different stuff. So here's print message. And if we've decided that it's a ghastly error, as opposed to something we can recover from, then, and in this case I've used access denied, then we'll say, oh, well, we can't find such and such. And then I've printed some stuff so I can crib a little bit and make the whole thing easier to write the exploit for and do the demo. And then we're going to call fprintf, and that's where the real problem is. So we're just going to, bam, print whatever's in the buffer, and then we'll call the error function, which is either recoverable error, which says, hey, you can fix this, or, oh, no, we can't fix this at all. And so then we're going to just exit straight out, okay? And that's kind of a bad practice as well. So that's what our application looks like. And now let's see what we can do with it. So I can all right, so this is what it's going to look like. It's going to tell me where the address of foo is. I'm going to try and make my execution jump into foo. Foo isn't called from anywhere. And if I can jump into foo, then I have altered the path of execution of the code. And so it says, yeah, something went wrong. I can fix it. Well, now, what happens if instead of trying to open stuff, I try and open %x%x, and you see the first time I printed out what actually got input, and then error function says cannot find O2. What's this O2 rubbish? I asked for file %x%x. Well, this is a clear sign of a format string vulnerability. Okay, so now what I've done here is things get a little bit complicated, and so I've resorted to a Perl script because it makes life easier on me. And so now I've got this very, very long argument with a whole bunch of x's, and at the very end I've got a %p. That's going to show me where it is that I'm actually writing to. And then I've got an ABC to show what my tag is. So okay. So what I've got here is, let me scroll it up a bit. Okay, so what I've got here is you can see at the very end of my output, it says cannot find a bunch of rubbish, 5782, that's %x's, all right? And then at the very end, you see 00, 43, 42, 41. And what that is ABC0 backwards. And the reason it's backwards is because we're working on a little Indian machine instead of a big Indian machine. And so what this does is it tells me that I've got my format string in the correct alignment. If I had put in one too many or too few %x's, I'd be seeing something like 43, 44, then 41, 42. Okay, so that's kind of what's going on. So now, let's try the second phase. All right. So what I've done here is I've given myself, one of the things I'm going to have to do is I'm going to have to try and give it a specifier that specifies a length that's very large so that I can actually modify the data. So all I've really done here is I've offset my string by adding in some dots, and then I've tinkered with things until I've got my desired 00, 43, 42, 41 down at the very end again, because that's my %p. It shows me where I'm pointing to. Okay. Now, we've got really an entirely different problem. Now we're actually going to start writing some memory. You see the %hn down at the very end? What I want to do here is I want to write 2 bytes somewhere in memory, whatever's pointed to by the end of this, all this, this stuff. And I've actually decided to actually start writing things. And so now we've made a little bit more progress. And it's claiming that it's inconvenienced us and wants to send a error message, so we'll tell it no. Okay. Now, this is the one that actually hacks things. And so what I've done here is gone back in and I've specified, let's see if I can find my mouse. I've specified the number of bytes until the exact point in memory that I wanted is where I'm writing. Now, I'm making this look really quite simple, but it took me a couple of days of thrashing around, reading people's papers, tearing my hair out, and quite a bit of cursing to actually get it done. And then just to make life even more fun, it worked great on my machine at home, but wouldn't work on the machine I'm doing the demo on as of this morning, so I had to fix it. Now here's something else. Note that I've altered the program execution flow. We've called the foo function, and it says, we've been hacked. And we exited gracefully. We did not blow up. That's because we were able to write exactly 2 bytes where I exactly wanted them. I didn't blow up any stacks. I didn't overrun anything. I surgically altered 2 bytes anywhere in memory. Okay. Now, the fix to this is really pretty simple, but the message I'm trying to get across here is if you have one of these problems in your application, you have a very, very serious problem because people can surgically alter very small chunks of your memory. You can couple a couple of these together to write a couple bytes here and a couple bytes there and pile it together, and now we're off to the races. I can also use this to read random bits of memory as well, and so that's a delightful thing from an attacker's standpoint, not such a good thing if you're the defender. Now, here's another one, and this is quite popular. People say, well, it's only an off by 1 error. How's that going to get me hacked? How are you going to put shellcode into 1 byte? And the funny thing of it is when I went to write the buffer overrun chapter for the 2nd edition of Writing Secure Code, 2 things I wanted to add were format strings and off by 1 errors. And I thought the format string, that's going to be easy, it'll take me an afternoon. And off by 1, well, that's some really intense stuff. That's probably pretty tricky. And so, it actually turned out to be quite the opposite. It took me an afternoon to get the off by 1 working, and it took me a couple days to get the other one working. So, got an example on that one as well. So here I've got some code that has an off by 1 error. The problem here is that I've used str.in copy, and I've told it to write the whole buffer, and there's nothing particularly wrong with the str.in copy call here. And then I've gone to terminate my buffer, and instead of saying size of buff -1, I've just said size of buff, and so I've actually written right off the end of my buffer by exactly 1 byte, and this is exploitable. And we're going to do the same thing here, is we're going to try and cause the code execution to run into the bar function, which will print out, I've been hacked, all right? So let's try it. And, okay, so now it's telling me that we've we've blown up. And let's not send a message. All right. So let's take a closer look at what's going on. And let me open the process here in the development environment. Okay, so that's gonna be a little bit hard to see. I apologize for this, but so let's see. I want to step out of that one, and so now I'm in my function where I'm causing the problem, and let's see what happens. So I'm setting up my call to string incopy right now. And then you can see my A's and 9s and 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. show up over here. And so then I'm going to write it. Now, this is something that's interesting. Let me see if I can highlight it and make it visible. There we go. You see the compiler has said that we're going to put 0 into the byte pointer pointed to by EBP. This is where the trouble starts, is the first thing on the stack right above the declared variables, at least when some versions of the compiler are used. This particular application was compiled with Visual C 6. When you compile it with .NET, it doesn't work anymore. The /GS switch, among other things, stops it. So we're going to put 0 into EBP, and then you can see that happen right down about the middle. See that red 0012FF, and now it's 0. That's going to tell us to jump back into our stack a little bit later on. So we'll just merrily continue along, and we're going to return right back out of here. And now we're back into main, and now we're returning out of main, and now we're going to move EBP into ESP, which is our stack pointer, pop it, return, and where are we? We're at 35, 36, 37, 38, okay, which was user-supplied data. Now, one of the interesting things about this is it has allowed me to specify an execution point anywhere in memory. It does not have to start with 0. So I can put us really just about anywhere in memory that I want to go. And so let's go over here and And we'll, so now we've blown up. And away we go. All right. We'll go ahead and kill the app and decide not to send an error report. And now, there we go. Bam. I've been hacked on a 1-byte error. And I think it's break time, is it? Or what's the schedule here? Okay. Well, we'll be back in just a bit.
15 minutes.
In 15 minutes.